What's up, students? I hope you're having the best day of your life today. Today, a lesson from the unit of modern physics, which is going to cover atomic and quantum phenomena. This is going to be good if you are taking the SAT physics exam, maybe an advanced placement high school course, or even just like an intro 101 first year type physics course. Is going to cover, that atomic and quantum phenomena in the topic of modern physics. In this particular video, I'm going to talk about the history of atomic theory. I'm going to talk about some major experiments and some scientists that you are going to need to know about, what photons are and how they transmit energy, the energy level diagrams, and some minor quantum phenomena. I'm going to define the photoelectric effect and the photoelectric experiment, and then I'm going to recap the video with all the formulas that you need to memorize for the SAT exam, because there is no reference table on the SAT exam, and other key points that I'm going to reference inside this video. So first, let's start with the history of atomic theory. So the ancient Greeks first proposed the word atom, and it was pretty much a name for an invisible unit of matter. And this was on a very, very basic level. And it wasn't until the 1900s, pretty much right at the start. So we're going to start, our modern era is in the 1900s. And everything that we're going to be talking about happened a little bit before this and a little bit after. And the first year that we're going to want to talk about, and it's not specific that you know exactly the years, but definitely know that this was at 1900. The first experiment and experimenter that we're going to look at, this was in 1897. And you'll remember this name from chemistry most likely. It was JJ Thompson. Now, JJ was awesome because he was the first one to show that an atom could be split. It was divisible. And he's also responsible, this is a big one, he discovered the electron. Now, we didn't know about protons, and we definitely didn't know about neutrons yet. But what JJ essentially said was that the atom had to be made up of positive and negative components, because he knew that the atom had a neutral charge. Now, I'm just going to say positive and negative components because we did not know about the proton. The proton had not yet been discovered or talked about yet. So his model of the atom, and like I said, you might remember this from chemistry, it was called the plum pudding model. Some people call it the raisin cookie. You'll see some other names for it. But essentially what JJ said was that we have an atom, and around that atom is going to be some negative charges, and then there's also worked in just going to be some positive charges as well. Like I said, no neutron, we just know positive and negative components that he figured were spread all around, distributed evenly. And this model really was not contested. I mean, it was 1897. We didn't know too much. Everyone was like, awesome. But then we found out that this actually wasn't correct by accident. And one of his students, one of JJ Thompson's students called Ernest Rutherford, once again, a huge chemistry name, he was working on something completely different when he made a discovery about the atom. Now, Ernest Rutherford used these things called alpha particles, which we later realized were just helium atoms. And they were pretty heavy. They were pretty dense. The helium atom has 2 protons. So this was a very, very dense particle. And what Ernest Rutherford, the experiment that he conducted, later became known as the gold foil experiment. Now, because these positive helium atoms were traveling through and they were so big, he pretty much expected them to pass right through the piece of gold foil and the atoms of the gold foil and not be deflected at all, because they figured everything would be distributed evenly in JJ's model, so the atoms would pass right through without being deflected. And what we found out was that was not true at all. So we had this gold atom, Au, and he was shooting helium atoms at it, alpha particles. And then he put a detector or a screen right behind it. And what he found out was when these helium came in, they were deflected upwards. Some of them passed right through. And some of them, in fact, bounced right back at him. And this shocked the heck out of him. Picture like shooting a cannonball into a paper towel, and the cannonball bounced back. There was this extreme amazement by him. So it concluded that there had to be something in the middle here that was really big and dense and able to deflect the alpha particles right back at him. And then as we got close to the center, it had to deflect it away. Now, that deflection, opposites are going to attract and like charges are going to repel. So this deflection away from the middle led him to believe that the center was a really dense, really dense positive charge. So what we need to know about Ernest Rutherford is this gold foil told us that there is a dense positive nucleus in the center of the atom. This also told us that this center nucleus was a positive charge. And by all of them that passed through, he said that a majority of this atom had to be empty space. And that on the outside of this empty space, the electrons were circling around this nucleus. So these two scientists right here, JJ Thompson and Ernest Rutherford, they laid the groundwork in the year 1900 to give us an idea of how the atom is going to be structured. Now, we knew that there was going to be more work to be done, but at the same time, there was other scientists doing other things on the atomic level, and it was pretty much those ideas that came together to form the model that we know now. So let's get away from the atom just a little bit and talk about what else was going on in that same year, 1900 essentially. So still in the year 1900, the next scientist that we need to know the name of is Max Planck. And what Max Planck was trying to do is he was trying to explain the color spectrum. Like, why are there different colors? And he pretty much said that light was created or emitted due to some atomic oscillations, so atoms moving back and forth. And essentially what he said was these atomic oscillations, they had a specific quantity of energy. And by saying that they became in specific quantities, he said they were quantized. So when you see this word quantized, or when somebody uses it in a sense, all it means is, if I were to say that the atom is quantized, that just means that it has a specific quantity of energy. That's all quantized really means. But more importantly, he created a mathematical relationship for these oscillations. And that relationship was based on a constant which is now known as Planck's constant. Now, Planck's constant is known as an H. Sometimes, guys, you might see some people write it with an H with a line through it, but on like the SAT and basic entry-level courses, just an H is going to be fine. And H has a value of 6.63 times 10 to the minus 34th joules times seconds. We can convert this into electron volts as well. So we remember that the electron volt, which is just given by a lower of E and a big V, this is a unit of energy. And essentially they created the electron volt because the atom is so small, like 10 to the minus 34th. Like that would be like trying to measure like a pencil with a ruler that was a mile long. Like, it just didn't make any sense. So they pretty much just came up with this conversion of an energy for an electron volt. And 1 electron volt is equal to 1.6 times 10 to the minus 19th joules. So knowing that, I can also say that Planck's constant can be represented by 4.14 times 10 to the minus 15 EV times second. Now, a few years later, in 1905, the boss walks into the room and says, "Hey, what are you guys working on?" And Max Planck explains to Albert Einstein exactly what he's talking about. And Einstein says, "Oh, I can now take this information and I can apply it to electromagnetic information as well, and electromagnetic radiation." And a whole bunch of new doors opened. So in 1905, we have Albert Einstein. So he also suggested that light is quantized. And remember, quantized just means has a specific type of energy. And it has like these little tiny massless like energy packets almost. And each little energy packet is going to be a different type of light across the entire electromagnetic spectrum, because we know that visible light is a very, very small part of the total electromagnetic spectrum. So Max Planck was just looking at visible light, but Albert Einstein said we can apply this all the way down here at the highest frequencies through ultraviolet, through the visible light spectrum, into infrared, into long radio waves. We can use this for the entire spectrum. And he called these little light packets photons. And he created a relationship, and this is a formula that you need to memorize if you're taking the SAT because you do not get a reference table. He said that the energy of a photon was equal to the frequency of that electromagnetic wave times Planck's constant. This was then expanded using the wave formulas. We know from waves that the velocity of a wave is frequency times its wavelength. So the speed of light is equal to frequency times wavelength as well. So now I can create an expression for frequency and say that that's the speed of light over lambda. So I can now rewrite my energy of a photon equation to be hc over lambda. So this is if you know the frequency. This is if you know its wavelength. These two formulas should go on your flashcards or however you are trying to memorize these formulas. So now a couple years go by and we are now in the year 1913. And the next scientist that we're going to talk about enters the scene. And this is another scientist that we are going to talk about. And his name was Niels Bohr. And this is really where we had the ideas of JJ Thompson and Ernest Rutherford combined with Max Planck and Albert Einstein to get a better look at what the model was, because we knew with the gold foil experiment there was still some holes or things that we couldn't explain. Like, we knew that electrons were negative and the proton was at the center, which was positive, but we weren't sure, like, why didn't those two things attract to one another? Why didn't the electrons fall into the nucleus? Well, Niels Bohr pretty much came out with a discovery and some ideas and suggestions which explained why that would not happen. And he said that the electrons were going around the nucleus in specific energy levels. And he explained that as energy was absorbed by atoms, these electrons would jump up energy levels and they would fall energy levels. And it was the falling of these energy levels which gave off photons. So let me draw exactly what I'm talking about here. So I'm going to draw a couple energy levels here. And I'm going to do circles the best I can. Okay, so these are the energy levels of an atom. So like here would be like the nucleus. Now this first energy level here, this is called the ground state. And this is where electrons, this is the lowest electron energy level. And we also call this N1. Now every level above the ground state is called an excited state. And I'll explain what I mean by excited in 1 second. But there's something we need to understand here. This is the first excited state, but it is N equals 2. All right, so sometimes that's confusing for a student. The second excited state actually happens at N equals 3. The third excited state happens to be N4. So we have to understand that ground state is N1. Then we have subsequent excited states. And we're going to, quote, excite the electrons by adding photons to them. So what's going to happen if I were to, I'm just going to draw these states now so you understand what I'm saying. So here's the ground state, and then this would be N2, this would be N3, and this would be N4. So essentially what happens is we have an electron that's down here on the ground state. And what's going to happen is a photon is going to enter the atom and give energy to this electron, and that electron is going to absorb energy and raise up to the next energy level. So the electron is going to travel away and its energy is going to be absorbed. When an electron absorbs energy, it is now called a photoelectron. And these energy levels, they have associated quantized energy amounts with them. So let's say, for example, this was minus 13.6 eV. This right here, we will say is minus 3.4 eV. This will say is minus 1.5 eV. And this will say is something called ionization. And that's 0 eV. Now think about this as like an elevator going down, right? So the number gets bigger, but I'm going in the negative direction. I'm going down into the ground. So for the electron to be absorbed, it needs to have the exact amount of energy to go up to here. So for this electron to absorb energy and go up to N equals 2, this photon would have an energy of 11.2 eV. Because we'd have this electron that's here, then I would give it 11.2 eV, the difference, to get up to here to make that jump. Now, if this was only 9 eV, the photon would not enter this electron and be absorbed by it. It would just pass right through. So we have to have these exact energy jumps for them to absorb energy and climb to the next energy level. So now we have that electron that's now called a photoelectron. It has some energy. Well, guys, nature is going to require or kind of want these electrons to be at a low energy state. So after they get excited, what these electrons are now going to do is they are going to fall back to the ground state. But now instead of absorbing energy, now this electron is going to emit energy. And this energy is going to be emitted back as a photon. So essentially we have a photon that enters. If it matches a specific amount of energy, that photon will be absorbed and it'll excite this electron up. Then the electron will say, no, I want to go back home. I want to go back to my ground state. It'll fall down and another photon will be spit out. Okay, so that's how light is created. Light is created when an electron or a photoelectron falls from a higher energy level down to a lower energy level. And every single atom has a different amount of energy between its energy states. So that's something that's important to know. Every atom, I'll call them energy gaps. Now, why is this important? Well, because if every atom has a different energy gap, that means that every single atom can only produce certain photons or certain types of light to leave that atom. So that's where we get into spectroscopy, where we're looking at the different spectral lines of an atom. And you did this lab in chemistry where you looked at neon lights through a spectroscope and you saw these different lines that gave off specific colors. These were like the fingerprints of the atom. That's how we can shine something at the sun and know what elements are there, because every element has specific energy drops, which is going to create different lights, and that's how we know what elements are present when we look at a certain light, right? Because we remember from just a second ago that the energy of a photon is equal to HF. The frequency of a light gives its color. So by knowing the emitted energy, I can then find the frequency, which is going to tell me the color that's created when I fall down to a specific ground state. Now, why are there 1, 2, sometimes 3, 4 different spectral lines? Well, because the electron has the opportunity to be absorbed all the way up to here, or all the way up to here, and then it can just fall down in a number of different ways. And those different ways are the opportunities or the different amount of photons it can create. I want to show you real quick. So let's say I have this photoelectron and it's been excited all the way up to here. Now think about a ball that's trying to like bounce down the stairs. The electrons are at the top of the stairs. They want to bounce down. I can create a different photon or a different colored light for every path down to the ground state. So for example, I can fall just straight down. So this would be the difference in energy from N3 down to N1. But if I'm here, I could also just fall down to N2. That would be another amount of energy that would create a completely different photon. Then when I was here at N2 chilling for a little bit, I could fall down again. Now this gap is going to create a different photon. So when I'm at N3, I can really fall and emit 1, 2, 3 different photons from that state. I could fall all the way down, which is going to create one color. I can go this way down to 2. That's going to create a second color. And then when I'm at 2, I can make another drop. And then I create a third different color. So for energy level diagrams, when electrons go up, they are called photoelectrons and they absorb energy. When electrons fall, they create photons, they emit energy, and each emitted energy is a different type of electromagnetic wave. And then as a side note, remember, to be absorbed, the exact energy must be met. Or the incoming photon that's trying to excite this electron, it just passes right through if I can't get an exact energy jump. Now back to this drawing I had before where I had this these lines going around. And I labeled this 0 eV or the ionization level. So essentially what happens is if I have an electron down here in the ground state, and here comes my little photon that's coming in. Well, if it gives this electron more energy, then that electron is going to be ejected out of the atom. So this electron is now gone. It's got more energy than this atom can hold. And when an atom gains or loses electrons, it is going to be called an ion. So an ion is really formed when a photon comes in and gives an electron more energy than the energy gap to here, to here, to here. It says, you are out of here. Have a great day. Go find another atom that needs an electron. Now in chem, we called this amount of energy the ionization energy. But in physics, it has a more fancy name. Well, maybe not more fancy, but it has a different name in physics. We call the ionization energy in physics the work function. This is an important vocabulary word, and its symbol looks like this. So the definition of the work function is just the energy needed to eject an electron out of the atom. So let's give an example here of how this exactly works and how we talk about it. Let's say at the ground state, that was listed at minus 10 eV. And I had an incoming photon of 12 eV. Well, we know ionization is at 0 eV. So we have kind of this energy initial plus the energy of the photon, which is really going to give the electron's final energy. So we have minus 10 eV plus 12 eV. We have 2 eV is going to be the energy of the electron after it leaves the atom. Okay, so from here to here, I needed 10 eV. But now there's going to be a little bit more extra energy up here of 2 eV. This extra energy right here has a name, and it's called K max. Okay, this right here is called the work function. This is K max, or the maximum kinetic energy. And I'll simplify this, guys, again, that the work function is really just the ground state. It's the absolute value of the ground state energy. And we're going to see these two related in just a second. So now if I see the energy of a photon, I can now express that in a different way. I can say that it's really the work function plus whatever K max is. Therefore, K max is really just the energy of a photon minus the work function. This is a formula you probably want to memorize. And also its variation, because we know that the energy of a photon, which we previously just saw, is equal to HF. So we can also say that K max equals HF minus the work function. Now, after making it this long in the video, you're probably bored to tears, and I'm going to give you some excitement now because there's got to be the question running through your head. I know when I was a student, it was running through like, okay, great, Brad, why? Why is this important? Like, why do we care about K maxes and things like that? And there is something very, very valuable to our lives right now, daily basis, that deals with all of these. So I'm going to bring this into real life right now for you. Thank you for sticking through the video. I'm going to give you at least something that's interesting. I'm not going to say it's going to set your hair on fire, but it's at least something interesting, and that is the photoelectric effect and how that relates to solar power. So I'm going to talk about the photoelectric effect and the experiment, and there's going to be some very key takeaways that you need to get from this information. Essentially, what the photoelectric effect talks about is we have a metal with a small, I'm talking very, very small work function or ionization energy. If I shoot a ton of photons at it, I'm going to get out a ton of electrons moving. And guys, what do moving electrons create? Well, moving electrons create current. So now essentially I can shoot light at a metal and create a current. I can now take photon energy and I can convert it to electrical energy. And guys, the photoelectric effect can be talked about in a number of confusing different ways. But at its core, it showed the ability for us to do this. Take incoming photon energy, light energy, and take that light energy, convert it into electrical energy by using the work function and ejecting electrons off of pieces of metal with the really small ionization energy. And here's how they do it. There's something called a photocell. Okay, this is essentially going to be like the battery, all right? It's going to create, a battery creates a potential difference, we learned, right? So if I have a metal with a very small work function, metal with a small work function, and what I do is I come in here and I shoot some photon energy at it, right? Which is a fancy name for light. Well, what's going to happen is when it strikes this metal, an electron is going to be ejected out of that metallic atom. Then over here, I have another plate. So this is going to act as the anode, if you remember a battery, and this is the cathode. So these electrons leave here. Now, what happens when an electron leaves an atom? Well, that's going to leave this as a positively charged plate. And if they get ejected over to here and this absorbs electrons, this is going to be a negative plate. Now, in between these two plates now, I'm going to create a potential difference, which is really just a voltage, V. So we have the sunlight comes in, it hits this specific type of metal plate with a low work function. Electrons get ejected off of it, and there creates a potential difference in here. So if I add a wire in between these two plates, I now can get current to flow. That, guys, is solar power. Solar panels are just really specific types of metal with a really, really small ionization energy. Sunlight comes in and blasts this thing, creates a potential difference. We put a wire right here. The electrons start to flow through. It's fantastic. But they wanted to test different frequencies and different amplitudes. And we remember from waves, guys, frequencies would be different colors. Amplitudes are different brightness. So what happens when I shoot different frequencies or different energies in? And what happens when I shoot this metal with brighter lights of the same frequency? How is that going to affect potential difference and current? So the photoelectric experiment tested potential differences and currents depending on frequency and amplitude. So first, what did the photoelectric experiment tell us about different frequencies? Well, it said at low frequencies, there was no V. Therefore, there was no electrons ejected. So essentially, if I had a frequency that was under the work function, there would be no ion created. But as we increased F, as F went up, energy emitted went up. After I went above and beyond the work function, so energy went up. And what that made potential difference do is go up as well. So when I was at a low frequency, no electrons were ejected because I was under the work function. Once I exceeded the work function and was able to ionize that atom, well, the higher the energy, as frequency went up, the energy went up, and therefore we created a larger potential difference. Overall frequency affected energy, which in turn affected potential difference. And they pretty much summarized this findings into a very, very popular graph that I'm going to sketch for you right now. So on this axis right here, we're going to have Kmax, and that's going to be in EV. Okay. And then down here, at the y-intercept, that's the work function. So as you see is when we have a Kmax that is under the work function, there was no electrons emitted, right? Because they were still in the atom and they were still bouncing back and forth. At this point right here, they call this the threshold frequency. And as we can see, this is once again where Kmax equals 0 EV. But then as I increased above and Kmax now became positive, the electrons were emitted, and the amount that were emitted were directly proportional to the frequency. Now some things to note. Remember I just said this. Kmax was really equal to HF minus the work function, right? I just derived this just a second ago, something that's very, very important for us to understand. This is set up as Y equals mx plus b. So we see that the slope of this is what, guys? Is h, Planck's constant. That is something very, very important to talk about the parts of this graph. So just to review what we're looking at once again. Here we're still in the atom. No ionization takes place. Photons are coming in, electrons are coming up, giving off, right? This is the work function. This essentially is the ionization energy right here, the threshold frequency. And once I exceed that, then electrons are going to be emitted in a direct proportion to its frequency. So that frequency is going to give it some Kmax, where Kmax is Planck's constant times that frequency minus this work function. And the slope of this is going to be direct because it's directly proportional to F. And that the slope of this line is going to be Planck's constant. So I remember from my test back in the day, they gave this graph and they said, what is the work function of this metal? And I remember it because I got it wrong. I just didn't know that the work function was simply just the ionization energy. So essentially, if I just take this formula here, well, I can say that Kmax at the threshold frequency right here is 0. So the work function is really just the threshold frequency times h. I just remember this was literally a question, and they gave a bunch of different types of options. It was like h over f or h times f. There was just probably a square root in there. But you have to remember that this relationship here allows you to find the work function of any metal, the threshold frequency times Planck's constant. So how did amplitude / brightness, how did this affect it? Well, what they found out when they increased the amplitude and didn't change the frequency, we found a whole new set of findings. By increasing the amplitude, we increase the amount of photons. Okay, now this increase in photons increased the amount of electrons being emitted. But, and this is super important, the V did not change. So I could not raise the potential difference by making the light brighter. I also could not change the energy. So all the amplitude did was increase the current. And the findings of this experiment lead to something which is probably the greatest takeaway from the photoelectric effect. This one, star, and remember, if you only remember one thing about the photoelectric effect, remember this. It showed that light waves act like particles, not waves. So remember from waves have certain phenomena that they follow. Diffraction, reflection, the Doppler effect, things like that. Light waves, they act like particles. This is so important. This photoelectric effect is what proved that light acts as a particle. So here are the takeaways that you really should know about. First, the scientists. It started with JJ Thompson. His student was Ernest Rutherford. This is plum pudding, and he discovered the electron, things like that. Gold foil experiment. We also had Max Planck, Albert Einstein, and lastly, Niels Bohr. We had spectral lines and energy level diagrams. So as electrons went up, they absorb. And when electrons fall down, they emit. And they emit photons. And then last, we had the photoelectric effect and experiment. And this shows increasing frequency, increases V and Ke, increasing amplitude, increased current. Formulas to memorize. Definitely E equals HF and its variations as well. E equals HC over lambda. And Ke max equals HF minus the work function. So right here, I'll leave a playlist with all the SAT physics videos. And as I build them up, it's going to start small. The content will build over time. Right here will just be a playlist with just modern physics. If you have any questions, guys, leave them in the comments below. If you learned something from this video, please give it a thumbs up. Have a great day.